In this video, we're going to go over the final two problems in the Arrhenius Made Easy packet. And one thing you'll notice about these is that they kind of incorporate a lot of the different aspects of the kinetics unit. Okay, so the first thing we're going to do is just to write balanced equation for decomposition of hydrogen peroxide. So we did this back when we did reactions. So H2O2, right? And we got water, and we got oxygen. And let's see, what do we need there? We need a 2 and a 2, right? So it's 4 and 4. Yeah. Okay. So then now it wants us to do a reaction coordinate diagram. So that's an energy diagram for this reaction. And so we've got several pieces of information in there. We have that our activation energy is 72 uncatalyzed, and I'm going to put the catalyzed, 28 catalyzed, and our total delta E is a negative 204. So I'm going to use that fact first, and that we know it's going to be exothermic. So my reactants could be up here, right, and my products are going to be down here somewhere. And so we know that difference is 204. And so just to kind of make our math easier, I'm going to put it at 0 here so that that'll be 204. Now we know that the products don't have 0 as their energy, but I'm just shifting it back to make our math a little easier. So then the next thing it says is that uncatalyzed our activation energy. Alright, so it's reactants up to, and it said that was 72 kilojoules per mole. So that means that that value there, or plus 72. Or the activation that was 28, right? Because that's how catalysts work. It lowers the activation so that more reactions can go forward. So here, if I look at instead, that's this value there is 28. So that means that that is going to be 232. Right? And so that's kind of all we can tell about this diagram. So our next question here is, what is the activation energy? I'll look at that, right? That would be uncatalyzed reverse. That is our reactants up to the top, which is 4276. And catalyzed 32. Okay. Moving on. All right. So, whoops. Some stuff left over on there. I'll leave part of that. But okay. So now in this problem number 6, we're going to combine Beer's law with kinetics. And that's actually what we're going to be doing in our next lab, is we're going to be doing a kinetics lab, but it's going to use the color of the solution and the way that it changes to measure the reaction rate. So we're going to use an equation. This is on your sheet, your formula sheet, and it lists it very generically. It's like capital A equals ABC. It has on the side that tells you that the little a is molar absorptivity, B is the path length, so that's the width of the cuvette. Then C is concentration, and capital A is our absorbance. We're going to use that equation to answer this question because we have the absorbance thus in the text our molar absorptivity and our path length, and then we're solving for our concentration. So when we do the math on that, divided by 2.75, 10 to the third, times 1, okay? So that gives me a concentration of 0.00012. That's this value right there, 0.00012. So now it says, all right, use our data for concentration and time to determine the order for the reactant. So, right, we've now got 1, 2, 3 concentrations that are paired with 3 times. So we can do our graph. So we're going to go to our 2 variable statistics and put in the time. We've got the 0, our concentration, the initial 6.25 10 to the minus fifth, 5 times 10 to the minus fifth. Okay, so we're going to go now to symbolic. I'm going to check zero order, first order, second order. Make sure everything else is unchecked. Okay. And my plot. And now I'm going to go to the number view and stats. Look at R squared values. Looking at those, our second order, R squared value of 999. And then again, if I were doing this on the exam, I would go back to my equation there. So I have 1 equals 7.6 x plus 8.5. So now, just to show them that I did indeed do that linear regression. Okay, so now it's like, what is the value of the rate constant? All right, well, we got it from our equation. K is equal to 776.2. And second order, so polarity of the minus 1. Oh, wait, it's 10 minutes. So let's make that right there. Minutes to the minus 1. So then here it says calculate the number of minutes it takes for the absorbance to drop from 0.330 to 0.096. So this is my t equals 0, right? So this is t. Remember our second order plot, y is over concentration, x is time. So this is a kind of a given absorbance. Concentration. So here all the times that this is an absorbance. That's not what I graphed. I graphed concentration. So I need to go back up to my data table. This is my concentration for the 0.096 absorbance. So I need that concentration, 3.5 times 10 to the minus 6. So my A is 3.5 times 10 to the minus 5th, which means that my y, right, is going to be 1 over that. 5 times 10 to the minus fifth. And I want to know for that, what is the x equal? So now I'm back using the solver. So I'm going to copy my equation to the solver, paste equals. For my x, so I'm getting that x is equal to 6 units. Okay. All right, and then now here it wants the half-life of the reaction. All right, so second order, right, the half-life depends on what you start with. So this doesn't specify. So I'm just going to do it for from the initial concentration. I'm going to go back up to my data because I don't remember what that was. 0.00012, all right, 0.00012. So now since I'm doing my half-life, right, the A at the half-life, or concentration at the half-life is going to be half. So 0.00006. All right, so remember my equation for second order is KT plus 1 over A naught. All right, and so 1 over 0.00006 is equal to 776.2 times t plus 1 over 0.0012. Okay, so let's do the math. 0.00 minus 1 divided by 0.0012. And so I'm getting a half-life of 10.74 minutes. Okay. All right. So now let's continue. Okay. So now we are getting into Arrhenius territory again because now we're given a rate constant and a temperature. So let's make our own little data table here. Temperature in Celsius and a rate constant. So this one it says at 35 degrees Celsius I have 1.15 times 10 to the fourth. And then from before, that one was at 25 degrees Celsius, and my K was 776.2. All right, so I got 2 points to do my Arrhenius plot. So I'm going to go back to my two variable statistics, and we're going to go over to temperature. So I have 35 and 25. My symbolic, I'm going to first and second order graphs. Arrhenius. Now, my temps are in Celsius, and my X is already set up to do Celsius, so I'm okay there. I'm going to do the plot. so my slope is 742 minus EA over 8.314. Okay, and we're going to go back, and I know I'm going to need this equation, so before we jump back, I'm going to copy. So copy, all right? So we're going to go back, let's get back to there, and let's do this calc. So negative 24.72 times activation in 5,705, and that's in joules. Okay, this one here, for Arrhenius, remember Y is natural log of K. My temperature, X is 1 over the temperature. So we're going to our copied my equation to my equation, put in the Y equals. X is 1 divided by, that's in Celsius, 45 plus solve, and I get that Y is equal to 0.876, which is natural log of K. So K is E to the 11.876, which is 11.876. So it's 143,774. And that, again, it's still second order, so that's molarity to the -1, minutes to the -1. Okay.